Hello, I'm Alan, and this is my work on the stress and strain characterization of seismic sources in California using moment measures of mechanism complexity. My talk is a continuation of the talk by Tom Jordan in this session where we discuss theoretical aspects of our research. Here, instead, I'm going to present practical applications of our theory. The motivation for our work is to understand how the mechanism complexity is determined by tectonic stress fields. When I speak about tectonic stress fields, I refer to moment tensor densities, which can be given by seismic sequences, or also the mechanism complexity in complex seismic sources. And a perfect example of that is the 2016 Kaikoura earthquake, which ruptured more than 20 mapped and unmapped faults in the alpine fault zone of New Zealand. The focal mechanisms in a seismic sequence are usually used for inverting the tectonic stress fields, meaning the orientation of the stress ratio. But here we are going to use these measures to also understand what is the expected complexity by a given state of stress and strain. For our formulation, we use the deviatoric stress tensor, which is given by the principal stresses sigma 1 to sigma 3, which also help us to define the differential stress ratio R. R is a parameter that is commonly used in the stress characterization studies. However, we are going to incorporate an extra parameter which we call kappa. For defining kappa, first we have to speak about how the moment is partitioned among a basis set. For example, if we integrate the moment tensor density over a volume, we can obtain the central moment tensor. If we consider the best double couple of that CMT can be defined by the outer product of the normal vector to the fault and the slip vector, but those vectors are the average over the entire volume. However, elementary sources can be oriented relative to this mean mechanism or these vectors. Thus, we can account for the moment from these deviations by constructing an orthogonal basis set. This basis set is constructed by orthogonal rotations from the CMT. Here I'm showing the moment tensors M1 to M4, which are given in the right-hand plot. We see that the CMT depends on the values of R. M1 represents variations of a strike if we consider a right lateral faulting. M2 describes the variations of rake, and M3 the variations of dip. M4 complements the basis set by accounting for the CLBD component that is not accounted on the CMT. This basis is physically motivated. In previous papers by Tom Jordan and myself, we speak about different ways of constructing basis sets that are of interest in seismological applications. As I mentioned before, we want to characterize the sensitivity of the strain to the stress fields. For that, we impose a probabilistic model of the stress distribution. We assume a probability density function of the scalar moment density, which is proportional to an exponential function. Here in this equation, kappa is the strain sensitivity factor, and n is the normalization constant, so that the probability function integrates to 1. If we have the discrete catalog of seismic events, we then project them onto the 5 basic members. This projection gives us the direction cosines, which can be integrated against the probability density function to obtain the moment fractions. Here on the right, I'm showing an example of the probability density function. We see that for kappa equals to 0, the distribution is uniform on the unit sphere, and then the faulting can occur in any direction. And as kappa starts to increase, the maximum stress starts to concentrate in the regions of maximum shear traction. As an example of the data processing, I'm going to use the data set from the Landers sequence. The Landers earthquake occurred in Southern California in 1992. The data was obtained from the COMCAT catalog from the USGS and has events from 1980 to 2020 in magnitudes 2 to 4.5. In total, the catalog for Southern California has about 43,500 events. The one in Northern California has 32,300. And for this example that I'm showing here, I'm using 7,800 events. So the steps are to obtain the average CMT, and from its best double couple, obtain the normal to the fault and the slip vector, and from the orthogonal rotations, construct the basis set M alpha. For alpha, larger than 0. Then we project the elementary mechanisms into this basis set to obtain the moment fraction and also obtain the shape factor, which is the shape factor is a proxy for the stress differential ratio. We obtain the parameters r and kappa by maximizing a likelihood function, which we construct from a logistic normal distribution. Here is an example for the Lander sequence of all the mechanisms in the red box that we can see here in the maps. In the panels on the left, I'm showing the distributions for the moment fractions. Here in red, I'm showing the distribution for F naught, which is the 0-degree term. F naught in blue is the distribution for the Aki moment. In blue and orange, we see the empirical distributions for F1 and F4 and their mechanisms. And similarly, in purple and green, we see the mechanisms and empirical distributions for F2 and F3. The lines are the fits to these distributions using beta distributions. In the bottom panels, we see the distributions for E naught, which is the shape factor. And in the next panel, we can see the correlation matrix of the moment fractions. In this correlation matrix, we can see that F naught is strongly negatively correlated with all the moment fractions of higher degree. Using the likelihood estimation, we find a moderate complexity. The estimated kappa is about 5.75 and R equals to 0.33. Another application of this methodology would be temporal monitoring. Here in the left, I'm showing the example that was in the previous slide where we estimated a kappa of 5.75 for the Lander sequence. This value was obtained for the foreshocks before the Joshua Tree event in 1992, which was a magnitude 6.2. And in the bottom panel, I'm showing the distribution of the principal axis. We see that the p-axis is mostly from 15 degrees from the north. The next panel shows the estimation of kappa and R for the aftershocks of the Joshua Tree event, but before the Landers event. We see again a moderate complexity, however, the value of kappa is larger, implying that there is less complexity. But something that is interesting about this, and it's been discussed in many studies, is that there is a rotation on the direction of the p-axis from 15 degrees to about 30 degrees to the east. Now, here I'm analyzing the seismicity between the Landers earthquake and before the Hector Mine earthquake in 1999. We see that for the aftershocks of the Landers earthquake, there is a high complexity. The value of kappa that we estimate is 4, and the value of R 0.37, which is not very different from the values before. But we also see that the p-axis goes back to about 15 degrees. Finally, after the Hector Mine earthquake, there is again a very high complexity, even higher than the aftershocks of the Landers earthquake, and the values of kappa drop down to 2.75. Here I'm showing the stress and strain characterization for all the seismicity in Southern California using the catalog with over 43,000 events. On the left, I'm showing the values of the differential stress ratio that we obtain. We see some interesting patterns. For example, for the San Jacinto fault, the value of R is around 0.5, and this implies that there is mostly a regime of transtensional stress. We see a similar regime on the entire Eastern California. So when we go to the west of the Mojave Desert in the Garlock Fault and San Andres Fault in the Mojave section, the value of R is larger than 0.5, implying that there is more compressional state of stress. In the panel of the right, we see the values estimated for the strain sensitivity parameter. The values of kappa range between almost 0 to 13 in the entire Southern California. In San Jacinto, we see values of around 7. In the Elsinore fault, we see values below 6, which imply moderate complexity. And the regions with larger complexity are to the west of the San Andres fault in the Mojave section. Here I'm showing the results for the seismicity in Northern California. On the left, I'm showing the values of the differential stress ratio. All the values are around 0.6 or above in the San Andres fault, the Calaveras fault, and in the Hayward fault, the values of R are about 0.5. So this implies that this region is mostly bilateral with some transpressional stress. There is some variability of R outside these faults, which is related with just the complexity that we see in the multi-branching of the faults. For the values of kappa, we see large values in the Parkville section, which is expected given that there is a large slip and the San Andres Fault is very well localized in this region. Similarly, high values of kappa are observed in the Calaveras Fault, and they continue up to the Hayward Fault. The other regions around the San Andres Fault, the Calaveras Fault, and Hayward are very complex. They have values of kappa smaller than 4. Given these results, we want to understand how the strain sensitivity parameter relates with other measures of complexity. And for that, I used the model of Powers and Jordan in 2010, who parameterized the distance of the seismicity to the fault using a power law function. The parameter of this power law function, d, is related to the thickness of the damaged zone. I took the faults in Southern California and made estimations of the parameters r and kappa. Here I'm showing the results of kappa against the distance from the fault, this parameter d, which is the thickness of the fault zone. We see some negative correlation, although it's not very strong and perhaps not very significant, as we have this cloud of data points for low values of d and moderate values of kappa. On the middle panel, I'm showing the values of r and kappa. You can see that for Northern California, most of the faults show moderate to low complexity. Those are the results for Southern California. They look quite different from Northern California. For example, the estimated fault zone thickness is larger for most of the faults. And also the values of kappa range from high to moderate complexity. We can explain this by looking at particular cases where the seismicity occurs in the conjugate planes. So this gives an apparent wider damage zone. In the middle panel, I'm showing the differential stress ratio against kappa. We see that for Southern California, R ranges over a wider interval, and the values of complexity range from high to moderate. So finally, I'm going to show the latest part of my study where I compiled cumulative offsets for different faults in Southern and Northern California. Total slip from faults in Powers and Jordan in 2010, and also in the study for Peterson and Wisnowski in 2004. Here I'm showing the values that they documented and the values that we estimated for the parameter kappa. We see a strong correlation between the maximum offset and the values of kappa. For some faults, for example, the Parfield, which has the largest offset, there is a very high value of kappa, which implies very low complexity. On the other hand, faults like the Newport Inglewood that have low value of kappa, they will show low values of cumulative offset. As conclusions, we developed a probabilistic model to characterize the stress and strain field for seismic sequences. Our model accounts for all the complexity on the CMT orientations, and we introduced a new parameter which we call the strain sensitivity factor, which describes the seismic strain's response to the stress. Kappa is related to other measures of fault complexity. We analyze the damage zone width and also the cumulative offset, where we found a strong correlation. This differential stress ratio is about 0.5 in Northern California and Southern California, but in Southern California we observe larger dispersion. This Southern California also shows larger complexity. Additionally, I also show the potential of our model to do temporal monitoring of seismic sequences, where we could look for strain concentration that might indicate a preparation phase for large earthquake. Thank you, and here is my email. If you have any questions, please contact me.